natural base E and the next component of compound interest, which is compounding continuously. Okay, so we know about compound interest. We know that compounding is when we recycle the interest process multiple times per year. Semi-annually would be twice, quarterly would be 4 times a year, monthly would be 12 times a year, and so forth. So the basic portion of that expression looks like this: 1 plus something over r, usually your rate over n to the n power. That's one of the components of that expression. There's more to it, but this is the basic structure. Okay, and what happens is the more times we compound per year, we approach a specific number. And you can see I took this structure and I just put different numbers in for x, just like you did in the activity that we did in class. And you can see it starts out with your smaller numbers around 2 for this expression. And then as x gets larger and larger and larger, I go up to 1,000,000 here, it approaches this number 2.718 and so forth. Okay, so that approaches that irrational number e that we looked at in the activity for compounding continuously. Okay, so you can see that on the screen here. It's an irrational number, like we learned about pi and square root of 2 and other things earlier in the year. It goes on forever without a repeating pattern. And it shows up in a lot of our exponential and what we see later logarithmic expressions and equations, just in natural settings. So it's not as famous as pi, but it has many impacts, just like pi in real-world application problems. Okay, so it's important to know, and it deals with when we compound continuously as our number of compoundings approach infinity. Okay. So we can approach this just like we do with many other exponential relationships. If I close this top part out and I look at it as an equation, y equals e to the x, and we look at the graph, you can notice that the graph looks very much like your regular exponential function. In fact, it's between y equals 2 to the x power. If you look at that, that shows up here in red, and then y equals 3 to the x power, which is here in blue. So you can see the difference here. It's closer to 3 to the x because remember, again, e is about 2.7. Okay, so you can see it's still an exponential function, and very close to 3 to the x. Okay. Now, to take things a step further, when you find out that something is compounding continuously, we change the structure of the equation to y equals p. Let me move this off because the graph doesn't make much of a help right now. Y equals p times e to the r times t power. So we're not going to worry about the graphing for a second here, but you'll see in the handouts that we do with this and the activities with this is the structure. All of these variables mean the same as what they've had so far in this lesson. P is your initial or principal amount, R is your rate as a decimal, T is time in years, and Y is your balance or your output amount after T years. Okay, and the only new component here is when they tell us it's compounded continuously, you use this natural base E in there. And obviously in this Desmos calculator, you can just type the letter E on your keyboard. On your calculators, you should be able to find an e to the x or e to the first button on the face of your calculator. A lot of times you have to hit second, but it should be there somewhere. Okay, so if you have any questions, obviously I can take a look at your calculator individually. Okay, so activities involving compound interest and compounding continuously involve this equation, and it's pretty simple to work with, just like the other ones, as long as you know where the E button is. Thanks for watching.